In this section, we're just going to review all the strategies we have for testing series for convergence or divergence. So again, our main question is, given a series, does the series converge or does the series diverge? To help us solve this question, we have the following tests. The test for divergence, which was one of the first tests that we uncovered, and that one said that if the terms don't go to zero, if the terms of the series do not go to zero, then the series has to diverge. So that's a quick thing to check. You just look at the series and you say, do the terms go to zero? Quickly take a limit of the terms. If they don't go to zero, then you know immediately it diverges and you're done. If the terms do go to zero, there's still more work to do. Again, the harmonic series is an example of this series where the terms go to zero, yet the series still diverges. So just knowing that the terms go to zero, not enough to determine convergence. It means there's more work to do. But this first part says always check to see if they go to zero, because if they don't go to zero, then immediately from the test for divergence, you know the series diverges and you're done with it. Okay, so now assume we know that the terms go to zero, so there is a possibility it can converge. Now what tests do we use? Well, if the terms are all positive, then we can either try to recognize it as a geometric series or a p-series. Maybe it's a telescoping series. Perhaps the integral test could work. Maybe the comparison test or the limit comparison test. So we have all of those possible tests to apply. If the series is an alternating series, then we'll look to use the alternating series test. Or we can check for absolute convergence if an is any real number. So whether it's alternating or not, or some of the terms could be positive, some could be negative, we'll go ahead and we'll try to check for absolute convergence, and that is either use the ratio test or the root test. And so those are all of our battery of tests that we can apply. So let's look at some examples. And for these examples, since this is a review section, I'm just going to quickly go through them. Some of them I'll just point the main methods of attack out. Others I may go through in a little bit more detail. But let's have a look. So let's look at the first one. Test the following for convergence. So we're looking at the sum of n times sine of 1 over n as n goes from 1 to infinity. So our first question, scroll back up here. Test for divergence. Let's always check that just to make sure, because if the terms don't go to zero, then we're done. And so we'll look at this one. Here our terms are an, which is n sine of 1 over n. And so let's look at the limit as n goes to infinity of those terms an. That is the limit as n goes to infinity of n sine of 1 over n. I could also write that as, and we notice in this case as n goes to infinity, this becomes essentially sine of 0 over 0, or this is equivalent to looking at this limit, sine as m goes to 0 of sine of m over m, which we know to be 1. That's our special limit we know about the sine function. So what have we shown? We've shown that the terms go to 1. And therefore, the series diverges by the test for divergence. If it's to have any hope of converging, the terms have to go to 0. So if the terms don't go to 0, we know it diverges. And so we're done with that one. Let's look at the next example. So the series 1 over 2 to the n plus sine of n. So in this example, I'll just partition this off. What do we know? Well, there might be a couple methods of attack here. Since this looks so much like 1 over 2 to the n, this sign just sort of affects the exponent by at most 1 or negative 1, depending on what the value of n is. It could be as big as 1 or as small as negative 1, so it's not affecting the exponent very much. I may want to compare this to a geometric series of 1 over 2 to the n, or something similar. So the first thing I'll note is that sine of n, well, that's at least negative 1. So n plus sine of n is at least n minus 1. And that means then that 2 to the n plus sine of n is at least 2 to the n minus 1, or the reciprocal of it is at most 1 over 2 to the n minus 1. So what I've just shown is that the terms of our series are bounded above by 1/2 to the n minus 1. And I know that a series with these terms, 1/2 to the n minus 1, that's a geometric series where r is a half. So I get by the comparison test that our series has to converge as well. So since sum of 1 over 2 to the n minus 1 converges, because it's geometric, then the sum of 1 over 2 to the n plus sine of n converges. And that was by comparison. Because we have this relationship between the size of the terms. An alternate method for this one? Well, we just noticed that the terms are all positive in this case. This n plus sine of n could be negative, but that just affects the exponent. So 2 to the power of n plus sine of n, still a positive number, reciprocal still positive. So I could check for absolute convergence of this series. And so I could perhaps try a root test. That would allow me to perhaps deal with those things in the exponent. So I'm going to go for a root test. The nth root of an, and take the limit as n goes to infinity. And that's the limit as n goes to infinity of the nth root of 1 over 2 to the n plus sine of n. And so that's the limit as n goes to infinity of 1 over 2 to the 1 plus sine of n over n. And now as n goes to infinity, sine of n, well, that's just bounded between -1 and 1. The denominator n is blowing up, so you get something that's bounded over something that's blowing up. So that goes to 0. So the denominator is getting big and the numerator isn't. So that's going to 0. So the result is that the limit is a half. And a half, well, that's smaller than 1. And so by the root test, since the limit of the nth root of the nth term is smaller than 1, then we know the series converges. So our series converges. So what we found so far is this diverges and this one converges. And for that second one, again, we had two different methods. We either did a comparison with a geometric or we did a root test. In general, there's always more than one way to solve one of these problems. Which way to choose really depends on your experience, the kinds of things you know about series, how much practice you've had. I mean, this all sort of factors into how well you can pick out whether it converges or diverges. Let's look at the last example. So in this example, we're looking at the sum of -1 to the n and ln of root n, where n goes from 2 to infinity. First thing I notice here is that there's this -1 to the n, so it's an alternating series. And so let's try the alternating series test. Here the bn's, the positive part of each term, is 1 over n ln root n. And we can see that these things are decreasing just because everything involving n is in the denominator. Bn's are heading to 0. They're actually decreasing to 0 as n goes to infinity. And those are the two properties we need to apply the alternating series test. And so by the alternating series test, the sum of negative 1 to the n over n ln of root n converges. Because the positive part of the terms are decreasing to 0. And so by the alternating series test, we know that the series has to converge. So that gives us that this converges. But there is a deeper question here. The deeper question we could ask is this series absolutely convergent? So in this case, we want to know about the convergence of this series, where we don't have those negative 1 to the n's appearing. And of course, just knowing that the terms go to 0 in this case, that in no way guarantees convergence. The harmonic series, again, is one of these examples. Terms go to 0, yet it diverges. Only in the case where it's alternating do you get any information about when the terms go to 0, but whether it converges or not. Now we're stripping off those alternating signs and focusing just on the absolute values of the terms of the series. Is this series absolutely convergent? In other words, is this series down here convergent? Well, let's have a look. One thing I can do is I could rewrite log of square root of n as 1/2 log n by bringing the exponent down. And then I'll bring the fact that there's a 1/2 in front, all the way up front as a 2. So this I can rewrite as 1 over n ln of n. And so now is this series convergent? Well, how could we deal with that one? We could use the integral test. And the integral test would tell us that it diverges. We in fact saw this example when we did the integral test. So there's an example where we want to check absolute convergence. We get to a series that we can apply the integral test to. We get that that series diverges, and therefore the series of absolute values diverges, yet the original series where you had those signs in there, that converges. So the reason the original series converges was because of the fact that there was those negative signs alternating through it. Because if you remove those, then the series no longer converges. So therefore, that alternating series conditionally converges. It's not absolutely convergent. It only converges because of those negative signs in it. So it's conditionally convergent.